Hey guys, we are kind of getting underway in our trig unit, and today we're going to talk about arc length and circular motion. Basically, these are just fancy words that discuss things like circumference and area and how they can be made more refined, I guess, using trigonometry, using things we've learned about radians recently. So for this first example, I'm giving you a formula called arc length, okay? And in the arc length formula, it states that if you want to find the length of a segment around a circle, so the arc is like from here to here, you are going to take the radius of that circle and you're going to multiply by the angle right here, but it has to be in radians, okay? It has to be in radians. So this formula is not real complicated, not real difficult to use, but before I show you how to use it, I would like to show you something that's more familiar. And since we're discussing arc length, which is a distance measurement around a circle, let's talk about something you know called circumference. So hopefully you remember circumference is equal to 2 pi r. And so that's just telling you how long or what the distance is around a circle, right? If you look closely at the circumference formula, it is exactly written to the same format as this arc length formula. So S is arc length. That just means a little wedge of a full circle. Circumference, the same thing. It's just all the way around. R is radius. We have an R is radius here. And then it says angle in radians. Well, the angle all the way around a circle in radians is 2 pi. So this is just arc length, okay? So I'm going to show you two ways to do these arc length problems. I think one is a little simpler than the other, but one method is probably going to you're going to prefer one over the other, and that's fine. You just decide which method makes the most sense to you and then do it that way. Okay, so here is option one. Option one is I can, instead of doing the arc length formula, I could just look at this in terms of a circumference problem. So let's start with, what's the circumference of this circle? Well, the circumference would be 2 pi times the radius. So we'll call it 4 pi for now. Well, I don't need the whole circumference. I just need this little wedge. So what I'm going to do is figure out how this wedge relates to the whole circle as like a fraction. So 60 degrees in relation to a full circle is 1/6 of a full rotation, right? 60 is 1/6 of a full rotation. So I don't need the whole circumference. I only need 1/6 of that to get the area, or sorry, the length of this arc. So you're going to take your circumference that you found for the whole circle, and you're going to multiply by 1/6 because that's how big this wedge of this circle is. And you're just going to simplify that answer. So we would get 4 pi over 6, but that reduces to 2 pi over 3. And so that's your arc length here. S is the letter that we use for arc length, 2 pi over 3. And I don't have it written as a decimal anywhere, so we'll just have to stop with that. 2 pi over 3 is the answer. Okay, so that is method number one. Here's your second method option. So we're going to draw another 60-degree angle. And again, nothing real special about this. It doesn't have to be perfect. And we are looking for the arc length. The radius is 8. Okay, so if I want to use a more traditional route, meaning if you would rather just use the formula, let me show you how that looks. So the big thing with the arc length formula is that the angle measurement that's given has to be in radians. So how do you convert 60 degrees into radians? Well, we actually already learned this in Unit 4. You multiply by pi over 180. When you do that, the degree units of measure cancel, leaving you with only radians. And you get 60 pi over 180. Of course, that reduces down quite a bit. Finally, fully reduced would be pi by 3. Okay, now once you get that, then you can go ahead and plug in the r and the theta to the formula. So r is 8. And theta is pi by 3, has to be in radians. And so we end up with 8 pi over 3, and that would be centimeters. That's not simplified or unsimplified. And then as a decimal, it would be 8.377 approximately. Okay? Let's look at a couple others, not straightforward questions this time. So for example 2, this time we have a 100-degree angle, slightly bigger than 90. And the arc of the circle created, wow, that was bad, created by that angle is 9 inches long. What is the radius? So we're going to write down our arc length formula, and we're going to plug in what we know. And we know that 9 is the arc length, and we don't know the radius. Theta is 100, but theta has to be in radians. So this is where you're going to go off to the side, and you're going to convert your angle measurement to radians before you plug it in. So this would be 100 pi over 180. And simplified, that would be 5 pi over 9, I believe. And so that's the angle we're going to plug in for theta, 5 pi over 9. Now we're trying to find r. So from here, dividing would be the next step. Or you could break it up and do it in 2 steps. You could multiply by 9 first, which would give you 81. And then you could divide by 5 pi. So you would get 81 over 5 pi if we didn't want to simplify. And if we did want to type in a calculator, we would get 5.156. And that is a distance measurement, so we're using inches again. Okay, one more of those. This last example, the angle is unknown. So we do not know what theta is, but we do know the arc length and the radius. So stick with your formula. Plug in what you do know. You know the length is 8 and the radius is 5. Divide to find your theta value. Now, remember that theta is always in radians. So it'd be 8 over 5 radians. However, it says in the directions to convert to the nearest degree. So we would need to take 8 over 5 and convert to degrees by multiplying by 180 over pi. Okay, and the reason you want 180 to be on top is because you want these radian unit of measure to cancel. So you end up with, let's see, if you do all the math in your calculator, it'd be 8 times 180 divided by 5 pi. That would be about 91.673 degrees. But it says to convert to the nearest degree, so 92 degrees. Okay, so that's arc length. There's a couple questions on your homework that are like those. Next thing. Linear velocity. So this is just speed, okay? How fast are you moving? Linear velocity is how fast something moves. It's about direction, okay? So you're running or you're driving or something like that. There's a formula you should have learned in science class a long time ago for distance, called the distance formula, the science one, but it's d equals RT, which means distance equals rate times time. Well, the linear velocity formula is essentially the same thing, except we're kind of focusing on distances that could possibly be in like an arc length situation. So instead of D for distance, we are saying that that could possibly be S as an arc length, but they understand they represent a distance measurement, both of them, so they're interchangeable. R means rate, that means how fast you're going. In this formula, it's called V for velocity. Again, rate and velocity are the same thing, so it's, use R, use V, whatever, it's the same. And then T is time. So really, this S equals VT formula is just the same as distance equals rate times time, okay? Now, the equation has also been written in a different way, just solved for V. I wouldn't worry about that so much. It's pretty easy to solve for V on your own. So basically kind of focus on S equals VT or D equals RT, and you should be good. So we're just going to do one example of this because this isn't too terribly difficult. The biggest hurdle, I think, with questions that are related to motion or dimensional analysis like this one is the units of measure not matching. So here's what I mean. It says if you travel in a car at 65 miles per hour, how far did you go in 10 seconds? Well, the one measurement is in relation to hours, and then the other is in seconds. So we got to kind of get on the same playing field before we can plug anything into that linear velocity formula. So here's what we're going to do, okay? And this might be a little bit of a learning curve for some of you. So we're going to start by writing 65 miles per 1 hour. That's what this means, right? 65 miles per hour. In order for this problem to work, I need the hours to change to seconds. So we're going to do a conversion, okay? So what you want to do is you want these hours on the bottom to go away, and you want it to be seconds. To do that, the process is you're going to find a way to change or to put hours on top so that that unit of measure cancels, and then something else on bottom. So I'm going to do this in baby steps. You probably could find a way to do it a little faster, and that's fine too. But let me show you how I would do it. I would start with kind of like stepping down from hours to get to seconds, one step at a time. So something like 1 hour is equal to 60 minutes, right? Does that make sense? 1 hour is equal to 60 minutes. Well, from here, the hour unit of measure would cancel, but now we would be in minutes when we actually need seconds. So we're going to go another step. I'm going to put minutes on top, so it cancels with the minutes on bottom over here. And I'm going to say 1 minute is equal to 60 seconds. The minute unit cancels with this minute unit. And if you look at whatever the units of measure that are not canceled, you are left with miles on the top and seconds on the bottom. And that is what we want because we want to be able to relate the 10-second measurement to this problem. So we're going to continue, and that means we're going to multiply all the stuff on the top together, which would be 65 times 1 times 1, and that's miles. And then multiply all of the bottom together, so that would be 3,600, and the unit of measure there is seconds. And then divide. 65 divided by 3,600 is about 0.01805 miles per second. Okay, you're traveling 0.018 miles per second. All of that work was so that we could plug it in to our linear velocity formula. And remember your linear velocity formula, S is your distance. That is what we're trying to find. How far did you go is distance. Velocity is 0.01805, and that is in miles per second. And we're multiplying by the time, which is 10 seconds. And I'm going to put it over 1, so I'm looking at a fraction times a fraction. Okay? So when you go to do the math and multiply these two things together, understand that the units, seconds on top and seconds on bottom, cancel each other out. And the only unit of measure left is miles, which is what we want because we want our answer to be a distance measurement. Okay? So if I multiply this by 10, I would get 0.1805 miles. So about 2/10 of a mile is how far you traveled in 10 seconds. Okay, let's look at another problem that's somewhat similar. So angular velocity. Back here, this was linear velocity, so straight line movement or distance movement. Angular velocity is how fast is still speed, but it's how fast something rotates. Okay, so let's write that down. How fast something rotates. So think of like a wheel. In this example, they talk about a bicycle and the wheel spinning. That's what you're looking at, like how fast is that wheel spinning? So there's some new letters introduced in this problem. You will notice the formula itself, if you look right here, the formula here is very similar to the linear velocity formula, at least in the setup of it. So in this, theta is your angle. So theta is your angle, central angle of the wheel. That needs to be in radians, just like before. This weird W is actually a Greek letter. This weird W is a Greek letter. It's called omega. And omega is going to represent your angular speed. So how fast you're rotating is called W or omega. And then T is time. Okay, so example 5. If a central angle spins 15 pi radians in 8 seconds, how fast is the angle spinning per second? So we're going to start by looking at angular velocity. So I'm going to start with either one of these formulas will work just fine. So we'll go with this one. That's supposed to be theta. There we go. So the angular velocity, or the speed, which is what they're asking for here, is equal to the angle, how many times it has spun, and what that angle measurement is, divided by time. So in this case, 15 pi is that angle, and time is 8 seconds. So we could just type in a calculator and get 5.890. By the way, the units for this would be radians divided by seconds, and so that would be radians per second. Okay. Quick summary, linear velocity has dimensions of length per unit of time. So feet, miles, meters, all per some kind of time measurement. And angular velocity is going to be some kind of angle measurement. So revolutions per minute, radians per minute, degrees per minute, something like that. Okay, so here is an angular velocity, 60 revolutions per minute. 60 revolutions per minute. What we're doing in this example is we're just doing a conversion. So we're not finding the angular velocity that's already been given. We're not using a fancy formula. We're simply converting units. Okay, think of like converting days to minutes, something like that. We're converting from revolutions to, per minute to each of these. Okay, so for the first one, we want to change it to radians per minute. That's actually not too bad because they both already have minutes as the time unit of measure, so we don't have to change anything there. We have to change the revolutions into radians. Okay, so this is kind of like a puzzle where you're going to have to come up with ratios that allow you to relate those two things. Okay, so in your head, you got to think, how do revolutions around relate to radians? Well, think about circles, okay? If I go around the circle one time, that's called one revolution. What would that be in angles or in radians? One revolution is equal to 2 pi radians. So we're going to make a ratio out of that. We're going to make it so that the revolutions cancels. So I want to put the other one on the bottom to make that cancel. And we're going to put radians on the top. And we said 1 revolution is equal to 2 pi radians. Does that make sense? So that's going to be the ratio that we use to get the conversion that we need. Again, I want to make sure that the revolutions cancels on top and bottom, and I'm left with radians on the top because that's the first thing listed here, and minutes on the bottom because that's the second thing listed. So mathematically, once you get to this point, you just need to multiply top times top, bottom times bottom, and then you're done. So top times top would be 120 pi radians over 1 minute, and you would divide 120 pi divided by 1, but that's just 120 pi. So we'll call it 120 pi radians per minute. Okay, let's try that again. So now we want to go from revolutions per minute to degrees per second. So 2 things have to change. Let's start with the original statement that this is 60 revolutions in 1 minute. 2 things have to change. Revolutions has to change to degrees, and minutes has to change to seconds. So I'm going to start with the revolution part because we kind of already did that before. So think again about 1 revolution. How could I relate 1 revolution to degrees? Well, 1 revolution is equal to 360 degrees, right? So that's going to be the ratio that we use there. And I like to go ahead and cancel the units so I have a better idea of where I'm at. So right now, if I had an answer, my answer would be in degrees per minute, okay? The next thing I need to do is change minutes to seconds. So how do I change minutes to seconds? Well, I want the minutes to be on top so that it cancels with the minutes on bottom, and seconds to be on bottom so that I'm left with that for my answer. So I could say, let's write a ratio. How do minutes relate to seconds? Well, 1 minute is equal to 60 seconds, right? 1 minute is equal to 60 seconds. So then if I look at my units, minutes cancels with minutes, and I'm to a point now where I'm left with degrees on top, which is what I wanted, and seconds on bottom, which is also what I wanted. So we can do all of the multiplying now. Top times top, bottom times bottom. You get 60 times 360 divided by 60, which would just be 360. And the units are degrees per second. Okay, one more quick thing and we are done. So this is area of a sector, this means like a wedge of a circle. I want to remind you that to find the area of a full circle, you do pi times the radius squared. The area of a sector is just if you wanted to cut that into a wedge, okay? Again, take a look at this formula and how it relates to the area of a sector formula. You have radius squared in both. Theta is the angle measurement. Well, theta around a full circle is 2 pi, and half of 2 pi is pi. So again, this area formula was probably created by this area of a sector formula, or maybe vice versa. But they are pretty much the same thing. But this one's for a full circle, and this one's for just a portion. Anyway, same rule applies. Your angle has to be in radians. So let's start this problem because I already see the degree measurement. So we're going to go ahead and change this angle into radians real quick. And that's going to be 5 pi over 18 once it's simplified. And then you can just plug in and go. So area equals 1/2 times the radius squared times your angle of your sector, which is 5 pi over 18. And pretty much is straightforward. You're just multiplying that stuff. So half of 4 would be 2. Multiply this stuff. I'll go ahead and just put the decimal answer that I have, which is 1.745. Units would be feet squared because it's an area measurement. Okay, and that's it. So the homework is already posted. It's, I think, I don't know, maybe 10 questions or something. If you have any trouble, let me know. I know there's a few tricky questions on there. So just let me know through email or something if you need any help.